Today, we're going to be discussing Newton's second law for rotation. Remember from mechanics that Newton's second law for your linear motion is that the sum of the individual forces acting on an object, which we simply call the net force, is equal to the mass of the object times its linear acceleration, a. We know that torque can cause angular acceleration, which is different than the linear acceleration in Newton's second law above. We know that torque is the position vector crossed with the forces. So taking the cross product of this equation above with position on both sides gives the sum of the position vectors crossed with each force is equal to mass times r cross a. We can simplify this a little bit by recognizing that the magnitudes of the angular and linear accelerations are related. In particular, the magnitude of the linear acceleration is equal to the magnitude of the angular acceleration times the position vector. In addition, this cross product on the right-hand side, r cross a, is going to be perpendicular to both the position vector and to the linear acceleration of some point on the object by the properties of cross products. But that's exactly the direction that the angular acceleration points in. So putting this all together, we get that the sum of the individual torques on an object is mass times radius squared times the angular acceleration of the object, where one of these factors of the radius squared comes from the original equation, r cross a, and the second one comes from substituting the angular acceleration in for the linear acceleration. However, for a point object, we know that mass times radius squared is simply the moment of inertia. So finally, we have that the net torque is equal to the moment of inertia times the angular acceleration. This is exactly Newton's second law for rotation. Let's do a brief comparison between the linear and rotational forms of Newton's second law. So in the linear case, force equals mass times acceleration, I can view mass as sort of how hard it is to speed up an object. So if I have an object with very large mass, it takes a very large force to start it moving. In the rotational side, torque equals moment of inertia times angular acceleration, I can view the moment of inertia as how hard it is to spin up an object. So again, an object with a very large moment of inertia will require a very large torque to get it to start spinning. Thus, in the linear case, a larger force or a smaller mass leads to a larger linear acceleration, and in the angular case, a larger torque or a smaller moment of inertia leads to a larger angular acceleration. However, in both cases, force and torque are vectors, so they can either change the magnitude or the direction or both of the linear or angular accelerations. Let's look at a brief example of how these can change either the direction or the magnitude of these velocities. So consider these three cases of two vectors each. So first, suppose that the top case represents the linear velocity of an object, and the bottom represents the linear force applied to the object. Remember, Newton's second law in linear form says force equals mass times acceleration, so the acceleration of these objects will be in the same direction as these bottom vectors. So in case one, the acceleration is in the same direction as the velocity, so the object will be speeding up, but it will not be changing direction. In case two, the acceleration is perpendicular to the direction of the velocity, so the object will not change its speed, it will be moving at constant speed, but it will be changing its direction. In this particular case, the object is moving up, the acceleration is to the left, so this object will be turning to the left while maintaining a constant speed. In case three, I have both a parallel and a perpendicular component. So in this case, the perpendicular component is to the left, the object is turning to the left exactly as in case two, and the parallel component is in the opposite direction of the velocity, so the object is also slowing down. What would happen if instead the top vectors represented the angular velocity and the bottom vectors represented the torque? Well, exactly the same thing. In case one, the torque is in the same direction as the angular velocity, so the angular acceleration and the angular velocity are in the same direction, and this object is speeding up its rotational motion. In case two, the angular acceleration is perpendicular to the angular velocity, so the rate of rotation isn't changing, but the direction of rotation is changing. And in case three, both the direction and the magnitude of the angular velocity are changing. Finally, a brief note on how you can change the direction of angular velocity, because angular velocity is slightly harder to visualize than linear velocity. So suppose you are spinning your key ring on your finger. If your finger starts off pointing straight up, the keys are spinning in a horizontal plane. If you tip your hand over so that your finger now points horizontally, the keys are spinning in a vertical plane. So in this case, your hand has actually exerted a torque on the spinning keys, changing the direction of the rotation. If your keys haven't sped up or slowed down their rate of rotation, then the torque has only acted to change the direction of the angular velocity of your keys. That's all.